Uh, okay, so before we get into the actual textbook content, I think it would make sense to kind of go through a few like prerequisite things that I feel comfortable that I can kind of explain in 15 minutes. So, uh, I would say this video is more for people who like have a programming language under their belt, but like it's probably like their first language is like Python or Java, where like memory management isn't quite as important or as stressed. And like for Python, for example, you wouldn't have used something like a compiler before. So just want to make sure everyone is kind of on the same page on these things. So compilers, memory, and bits. Just want to make sure everyone knows what that is. So starting with a compiler. This is a C++ book that we're working through. So generally speaking, we will be writing C++ code. So we'll have a file, for example, and we'll have some stuff in it. And we'll have some file name like file.cpp, CPP being the extension for a C++ program. And we can read that pretty well. It looks a bit funny, but it looks like English for the most part, so we can understand it. And this file will contain instructions. That doesn't matter. Instructions. I have to write bigger. Sorry. Instructions for a computer to follow. But although we can read it as humans, if you gave that to a computer, it's gonna have a hard time understanding what you've just said, what you're asking it to do. So we need a way of converting this guy into machine code, which you can think of just a file of ones and zeros that means the same stuff as this, but is something that the machine can digest and actually execute and work with. So in essence, we need a way of converting C++ code into machine code. Right? Something that we can understand versus something the computer can understand. And so what carries out this translation process, that is the compiler. So the compiler you can think of as like a translator, essentially, that translates C++ code into the machine code. And there's a lot of extra stuff with compilers, a lot of fancy things that can happen. How they work is very fascinating, but we can kind of treat it as a black box where it's just a translator. That's what I was thinking of. So if I ever use the word compiler, and you're not super comfortable with that word in your mind, just substitute the word translator. All right, one down, right? Nice and simple. Compiler is a translator. Next up is memory, and I think most people have like a pretty decent like notion that computers have memory. This idea, my computer has 256 gigs of storage, and my computer has 16 gigs of RAM. Like this idea of like computers have the ability to remember stuff is fairly familiar, but what should I actually think about in my mind? What should I visualize in my mind when I think of memory? Might not be as familiar. So specifically for programs, for code that we write that becomes something that a computer can do, a computer is generally going to have to work with data when working with a program. So you think of something simple like adding two numbers together. You give the computer two numbers. Before it can maybe add them together and show you the result, it has to remember those numbers. It has to write those numbers into memory. So you can think of memory as kind of like a box or like a big rectangle, and it's space essentially for the computer to write down data for it to remember, so we can use it later. So if I tell the computer, okay, can you add 3 and 7 together and tell me the result, it's going to be like, okay, wait, let me first write down 3 and then write down 7. And it's like, well, what do you tell me to do? I'll add them together, and then it will check, okay, yeah, 3 and 7, I have my numbers written down, and then it will add them together, figure out 10, and say, hey, my result is 10. So memory, you can think of as just a big rectangle where the computer is able to write stuff down, keep track of things, and use it to sort of manipulate data and come up with results that you want. Now, to go in a bit more detail, a bit more specific, memory is actually, it's more accurate to think of it as a grid. each cell, each square in the grid represents 1 byte. Right? I think most people are comfortable with bytes, bytes, kilobytes, megabytes, like that. A single grid is 1 byte, so very small. And each byte or each grid, each cell or each grid, each cell or each byte has a unique address. So by address I mean like literally you can think of like a house address. If this memory is like a street, each cell is like a house with a particular number. So this might be like number 0. We generally start counting from 0. Number 0, then number 1, number 2, number 3, and so on. Each byte has a unique address associated to it. So to sum up, memory is used to remember data. Each cell in memory is 1 byte, and each byte has a unique address. In reality, the addresses look a bit more complicated than 0, 1, 2, and so on, but to be honest, conceptually speaking, they are just numbers. Alright. Yeah, that's pretty much it for the second part. I think I'll keep this actually. I'll get rid of this. The last bit is on bits. And the way I probably think about this is, so I would say look at a particular byte, so one of the squares in here, and we'll like zoom into it, so we'll draw it a bit bigger. So this square is one of the squares, one of the grid cells from here. Just zoomed into it. Typically, when you look at a byte and you zoom into it and you look at it really closely, what you'll see are 8 switches. So I'll put like 8 little dots. 1, 2, 3, 4, 5, 6, 7, 8. I'll get rid of you real quick. Alright. And when I say switches, I mean literally this little sort of toggle thing that you can turn on or off. So this is a switch. Each dot is a switch. And these switches have the ability to be turned on or off. And I think most people have the notion that computers work in binary, like computers and binary go quite hand in hand. But why that's the case, like how computers work in binary, might not be particularly clear. This is pretty much where it is. This idea of each switch can be in a binary state, so you can flick it on. So an on switch, and an on switch represents a 1. And an off switch represents a 0. How these switches are actually turned on or off is like very high level like circuitry and stuff, so we don't really think about it. It's easier to visualize. Just imagine the computer is capable of actually switching a physical toggle up or switching it down, on or off. So hopefully it's clear from this that if I have 8 of these switches in 1 byte, this is 1 byte, then I am capable of creating some 8-digit binary number using these 8 switches. By just sort of flicking some of these digits up, some of these switches down, I can make some 8-digit binary number. So when I said, maybe the computer needs to write down a 7, when I say write down a 7, I don't mean, of course, taking a pen and drawing on itself. I mean flicking these switches so that the binary number you make out of these 8 digits represents the number 7. And understanding binary is also quite nice if you can do that. That makes life a little bit easier. But hopefully, this idea of we can switch these digits up and down to make that number 7 makes sense and is clear. Okay, so when we talk about switch in this context, this is basically representing a binary digit. Just box this off. So a switch, a physical switch here, is representative of a binary digit. And a binary digit
is what we call a bit.
So a bit is basically a binary digit or a switch. These three are kind of interchangeable in that sense. Switch, of course, is very specific to this context, but binary digit and bit basically mean the same thing. So if I ever say bit, I'm basically talking about either a 1 or a 0 stored in memory like this. Okay, so that's pretty much the pre-intro, the prerequisite stuff that I'd want to make sure people are comfortable with. This is primarily for people who sort of have a language under their belt and are relatively comfortable with programming concepts, but maybe haven't come across this specific stuff yet. And from there, now I feel a bit more comfortable sort of starting the actual stuff. So we'll get into that.